Welcome to this explainer. We're diving straight into something absolutely fundamental today, the incredibly fascinating building blocks of how things literally move in our world. Whether you're navigating seventh grade physics and just starting to map out the universe, or you're just looking for a fun refresher on the actual science of motion, you are definitely in the right spot. We're going to break down position and motion, and we'll be using the visuals right here on your screen to make everything crystal clear. Let's get right into it.
Here is our quick roadmap for today. First, where are you right now? Second, distance versus displacement. Third, average speed. Fourth, direction matters. And finally, reading distance time graphs.
Okay, let's kick things off with Section 1. Where are you right now? Seriously, how would you describe where you are at this exact second? If you really try to answer this, you might say, I'm a few feet left of my friend. Or maybe, I'm sitting in a house 2 blocks north of the school. Notice what you instinctively did there. You didn't just rattle off a solitary coordinate. You had to compare yourself to something else. Your location is entirely relative. And that something else has a special name. It's called a reference point. A reference point is basically the starting point you choose to describe the location or the position of an object. It is the absolute foundation for defining where you are. A complete description of your position will always include 3 things: a distance, a direction, and, you guessed it, that all-important reference point. Actually, if you change the reference point, your entire description of your position changes along with it, even if you haven't moved an inch.
This fisherman brilliantly illustrates why reference points are such a big deal when we talk about motion. Look at him sitting in that boat. Is he moving? Well, relative to his fishing pole, which is acting as our first reference point, the man is perfectly still, right? The distance between him and the pole isn't changing at all. But what if we shift our reference point to that buoy bobbing out in the water? The man's distance from the buoy is absolutely changing as the boat drifts. So relative to the buoy, he is totally in motion. Motion is literally just the process of changing your position relative to a reference point.
Moving right along to Section 2, distance versus displacement. We really need to untangle these 2 vocabulary words because students confuse them all the time. On one hand, we have distance. Distance tracks every single step, twist, and turn of the path you take. If your smartwatch logs your morning jog, that's distance. But on the other hand, we have displacement. Displacement couldn't care less about the winding path you took. It is strictly the shortest, straightest line between where you initially started and where you finally ended up. Let's test this out with a classic sports example. Imagine a baseball player steps up to the plate and absolutely crushes a home run. He jogs 25 meters to first base, 25 meters to second, 25 to third, and finally touches home plate. Simple math here, 25 times 4 means his total distance traveled is 100 meters. But what is his displacement? Think about his starting position versus his ending position. The answer might totally surprise you. It's 0 meters. Because his final position at the end of his home run trot is exactly the same as his starting position at home plate, the difference between them is nothing. His displacement is a massive, surprising 0. He traveled 100 meters, but he was displaced by 0 meters. Wild, right?
We can see the exact same logic playing out on a soccer field. Follow the dotted line. The player runs from point D up to C, which is 41.2 meters. Then she cuts over to point B, which is another 10 meters. Her total distance is 51.2 meters. But look at that solid arrow cutting straight across from D to B. That represents her displacement. Even though her legs ran over 50 meters, she only ended up 40 meters away from where she started. The only time distance and displacement are exactly the same is if you travel in one single, straight line without ever turning back.
All right, let's jump into Section 3, calculating your average speed. Now that we've mapped out our paths, we need to bring a clock into the mix and figure out exactly how fast our position is changing. Speed is simply the measure of the distance an object travels per unit of time. It's a ratio. But think about any real-world trip, like walking from the park to the library. You don't move at a robotic, unchanging pace. You speed up to cross the street, you slow down to check your phone. Because your speed is always fluctuating, we usually talk about your average speed over an entire trip. To find that average speed, you just follow these 3 simple steps. Step 1, take the entire total distance traveled. Step 2, find the total time it took to complete that journey. And step 3, just divide the distance by the time. The formula is V equals D over T. So if a girl runs 25 meters in 6 seconds, you divide 25 by 6, giving you an average speed of roughly 4.2 meters per second. Boom! It incorporates all her speeding up and slowing down into one helpful overall number. But here's the catch. Telling me you are moving 4.2 meters per second doesn't actually help me find you if I don't know which way you went.
Which brings us perfectly to Section 4, Direction Matters, Exploring Velocity.
This is a massive distinction in physics. Velocity is not just a fancy synonym for speed. Velocity takes your speed and simply slaps a specific direction right onto it. 50 kilometers per hour is a speed. But 50 kilometers per hour heading north, now that is a velocity. Because it includes both an amount, what we formally call magnitude, and a direction. In physics, we classify velocity as a vector. And let me tell you, we absolutely love to draw vectors as arrows. Think of it like a visual cheat sheet. When you see an arrow representing velocity, the length of the arrow visually shows you the speed, and the pointy end shows you the exact direction the object is traveling. So the crucial point to remember here is that velocity is highly sensitive. If either part of it changes, the whole velocity changes. Obviously, if you hit the gas and your speed changes, your velocity changes. But get this. Even if your speed is perfectly constant, say you're doing exactly 20 kilometers per hour on cruise control, if you simply turn a corner and change your direction, your velocity has mathematically changed. And now for our final building block, Section 5, Reading Distance Time Graphs. Reading distance time graphs is basically like having a superpower that lets you see a whole journey at a single glance. Check out this basic setup. We always have time ticking away steadily on the bottom horizontal axis, and distance increasing on the vertical side axis. As time passes, moving right, we track how far away the object gets, moving up. This specific graph shows a perfectly straight diagonal line shooting up and to the right. To read these instantly, you just need to memorize these cheat codes. First, a perfectly straight diagonal line means the object is moving at a constant speed, no speeding up or slowing down. Second, the steeper that line looks, like a really tough hill to climb, the greater the speed. A shallow hill is slow, a steep mountain is fast. And third, if the slope curves or changes at all, it means the speed of the object is actively changing. Oh, and a quick bonus code, if the line goes perfectly flat and horizontal, time is passing, but distance isn't changing. The object is completely stopped. Let's use those exact codes to trace this slightly more complex train ride together. For the first 3 minutes, the line curves upward, getting steeper, so the train is speeding up. Then, between minutes 3 and 5, it's a straight diagonal line, so it's traveling at a steady, constant speed. But look at minutes 5 to roughly 7. The line goes totally flat horizontally. The train has completely stopped, maybe waiting at a station. After that, the line shoots steeply upward again to the 10-minute mark, meaning the train sped up rapidly to finish its journey. See? You just read the entire story of the train ride without seeing a single word of text. It is amazing how visualizing data like that brings it to life. As we wrap up this explainer on position and motion, I want to leave you with a final, slightly philosophical thought based on the physics we just learned. Imagine you lived an incredible life, traveling millions of miles, exploring every corner of the entire universe for decades. But at the very end of your life, you eventually ended up going to sleep back in the exact same childhood bed where you started. No matter how massive the total distance of your epic life's journey was, your total displacement would be zero. By the strict laws of physics, did you ever really go anywhere at all? Keep that in mind the next time you map out your reference points. Thanks for joining me on this explainer. Keep questioning, keep visualizing, and I'll catch you next time.